In this second part of 6.1, we are going to examine the logarithmic functions, and we're going to skip approximately the first 10 slides. So what we're looking at in here is how we convert from exponents to logarithms and what relationship they have. We had f of x equals b to the x, and then the relationship to a logarithm is that they're inverses. So we have the logarithm in base b, and the exponent goes over here. It's hard to tell with the notation, especially on my PowerPoint here, but we usually have a logarithm of base b of x. So the base that was in our exponential function becomes the base of the logarithm, and then our common logarithm has a base of 10, so logarithm base 10 is what's programmed into your calculator of some number that we'll work on as we go through these. And oftentimes that 10 is ignored, so we just see the logarithm of x. If we have a natural log, we have the logarithm in base e of x, and it's hard to tell the way I'm writing this, but logarithm and x are all on the same line. E is beneath it. Same thing with my logarithm and x, 10 is beneath it, so that the base is definitely a subscript. And we often see the ln for natural logarithm. The letter e, that 2.718 big long number, is not included with ln, so we would just see something like the ln of x. So the relationship between logarithms and exponents, this is kind of complicated here. If we have 2 to the third equals 8, that's how we write it as an exponent. To put that as a logarithm, we would say we have a logarithm. The base of our exponent was 2, so that's the base of our logarithm. Logarithm in base 2 of 8 equals 3. So we need to be able to move backwards and forwards between these two exponents and logarithms as we work through this chapter. In a logarithm, we're thinking if we see, say, log 5, 125 equals x, we think 5 to what power equals 125? Well, the power would be 3. And so we'll move back and forth from exponents to logarithms and logarithms to exponents. So in this section, we want to figure out what these are. So if we think 3 to what power equals 81? Well, I think that's 3 to the 4th. 3 to the 4th equals 81. Yep, that equals 4. Okay, then in the second one here, I'm thinking 2 to what power equals 1 over 8? Well, I know that 2 to the third equals 8. And to make it a fraction, I would need a negative exponent. So I would need negative 3 to make it go into a fraction. Then on this, let's see, 5 to what power equals 25? Well, I know 5 squared is 25, but how do I make it have a square root involved? So if I have a square root here, I know 5 squared equals 25. But what do I have to do to counteract the square root? I need to square a square root. So first things first, get rid of my, first thing I need to do is square my square root. Then I need to square that result. So if squaring a square is taking my square root to the 4th. So I think this gives us something to the answer is 4. Okay, now let's see what we have here. I know with natural log I have a base of e, and I've got an e somewhere in my answer here. So basically I just want to, I have a base e, so I'm thinking e to the what equals whatever this mess is inside the parentheses. So I'm going to clean up that something inside the parentheses. That something inside the parentheses there has to be squared and then the cube root. So to make sure I square it and then take the cube root, that would be raised to the 2/3 power. So e to the what equals e to the 2/3? Well, that sounds like 2/3. Then in number 5, there's no base there, so it's base 10, and 0.001 is 1 over 1,000, which is also 1 over 10 to the 3rd. So if I take 10 to the negative 3, I would get 1 over 10 to the 3rd. Then for questions 6 and 7, they're using a property, I don't know if we went over it fully, but our base and the base of the exponent are the same, and so those are going to cancel each other out, and all we get is the number 8. In number 17, we have the negative here, and so that negative is going, it's going to impact my answer. I know that I have the base of my exponent and the base of the logarithm, they're the same. I don't get negative 6. I have a negative in my exponent, so I have a result of 1/6 because of my negative exponent. So it's a 1 over 6. Okay, so here's where we have all of our properties for a logarithm. And because a logarithm is an inverse of the exponential function, I'm going to take my exponential function, b to the x, and I'll call that g of x just so we don't get it confused. But what's happening here is all of our original properties for the exponential are getting flip-flopped for the logarithm. So for instance, the ordered pair that we worked so hard, where it was 0, 1, that was common to all of our exponentials, now it's 1, 0. Instead of having a horizontal asymptote, of y equals 0, it's getting flipped, so it's no longer y equals, it's a vertical asymptote at x equals. And then our relationship of b to the a equals c, that's our exponential, goes along with logarithm of base b to the exponent equals the exponent with the big number c. Those two go back and forth. They are inverses of each other. And here are the two rules that we were using in the last one, where if the base of the logarithm and the base of the exponential are the same, you just get whatever's left. We see them as properties or rules or very helpful points to follow with both logarithms and exponents. Keeping in mind the idea that exponents, exponential equations, are inverses of logarithms, there's a relationship over here with our exponential equation, that's this guy. There's our exponential, and then that has our horizontal asymptote and passes through the point 0, 1. Then our logarithmic equation is a reflection over the line y equals x, and it passes through the point 1, 0, and has a vertical asymptote instead of a horizontal asymptote. Not too many properties or real examples demonstrate logarithmic growth, but a whole lot of things in the real world have exponential growth or decay, and so it is important to understand what the graph of an exponential equation looks like. It's not quite as important to understand the logarithmic growth or logarithmic graph, other than it is an inverse of the exponential. So here are the properties for logarithmic. Again, this is helping us demonstrate the graph, and vertical asymptote, passes through that point, This one's growth, because b is greater than 1. This one's decay, because b is between 0 and 1. And we would take this single ordered pair and shift that up, down, left, right by our transformations. So we had this original exponential function, and we're going to try to find the inverse of it and then attempt to graph it. So let's see what we can do. Okay, so if we have f of x equals 2 to the x minus 1 minus 3, I'm going to list in order what is happening to this function into a series of steps. The first thing that happens is that we subtract 1. Second thing that happens is we have a base 2. And the third thing that happens is we subtract 3. And the reason I'm breaking them down is because I need to find an inverse that undoes those 3 steps in that order. So for my inverse, I need to undo subtracting 3 by adding 3. To undo the base 2, I need a logarithm in base 2. And then to undo subtracting 1, I need to add 1. So let's see if I can create an inverse that does this. If I have a logarithm in base 2, where I'm going to add 3, and then I want to add 1, I think that very nicely undoes what the first one did. Okay, now if I want to graph those, let's see, I'm going to go with f of x equals 2, the x minus 1 minus 3, and g of x equals log base 2 of x plus 3 plus 1. Alright, now for my exponential, I originally had an ordered pair on the y-intercept that I am going to shift to the right 1 and down 3, so it's going to be somewhere around here, my horizontal asymptote down here, and I'm going to have a graph that does something like this. Okay, now for my, oops, sorry, wrong color, let me try all that again. Okay, how about I do it in red? Starting at 0, 1, over, down, there's that main point, there's my horizontal asymptote, and exponential growth because my base is higher than 1. Okay, now my g of x, it's a logarithm, and so I need to have a vertical asymptote that I'm shifting 3 to the left, and the plus 1 means that my ordered pair is up 1. See, normally it was there, shift that over 3, up 1. There we go. And it's a logarithmic graph, so it looks something like that. And if you look at those two graphs, that's not a pretty bad reflection over the line. Here's my line, if I can get it in here, over y equals x. Not too bad. And here is it actually drawn in by people, you know, who graph these things for a living, and my graph doesn't look too far off from their graph.